In this video, we're going to continue looking at the polarity of molecules and look at some examples of a couple of nonpolar molecules and molecules that are polar that you might not expect either way. So let's look at this molecule, CF4. So I'm purposely picking something where each of the individual bonds between carbon and fluorine is very polar. Again, fluorine being our most electronegative element, we're going to have a very much a unequal sharing of electrons. The fluorine's really going to want to dominate the sharing of the electrons and hog them for itself. But when we draw the molecular geometry of CF4, you can double check me on this, double check this with Lewis structures to make sure I have everything right. But carbon's going to form 4 bonds and have no lone pairs, and so it's going to have a tetrahedral geometry. And so this is what we get. Now each of these bonds is going to be polar. And so we can draw dipole moment arrows pointing along each of these directions here. But one of the keys here is that all the angles here are equal. These are all equal to 109.5 degrees. And so because of the symmetry here, because all of these bonds are equally spread out around the central carbon atom, there is no net dipole moment for this molecule. This is a nonpolar molecule, even though all of the individual bonds are quite polar. Right, so each individual CF bond is very polar, but because all of the fluorines are equally spaced around our molecule, so all these fluorines around here, they all, just like in the carbon dioxide example, cancel each other out. And so there's no net dipole moment, and this is a nonpolar molecule. So even though we can have very polar individual bonds inside of the molecule, that doesn't necessarily mean that the whole molecule is polar. All right, let's look at one other example, and then we'll look at a table with a bunch of examples. And that example is ozone. So we've looked at ozone multiple times for various reasons. All right, so we get something like this. Now, I want you to pause and think, is ozone polar or nonpolar? It's got a bent geometry, and just want you to think about that. Okay, so whether you said yes or no, I want you to sort of justify why did you think of that. And the answer here is that ozone, not benzene, ozone is a slightly polar molecule. Now, why is that? It's because of the fact that it's a bent geometry. So the fact that we have this extra lone pair of electrons here imbalances the molecules. So even though these individual bonds here, right, each of these bonds here is not polar. Right, there's an oxygen-oxygen bond is not a polar bond because they're the same. They have the same electronegativity. The fact that there's this unbalanced lone pair on this side over here means that the balance of the electrons is not evenly spread out. And so there's actually there is a slight dipole moment here. Now, it may be a little bit tricky, like which way does the dipole moment point? We actually end up with an imbalance in charge slightly towards the bottom, and that's because you just have lots of extra electrons on these. You have even more lone pairs on these oxygens down here. So this is a polar, and the negative side is down here. The positive side is up here. Again, it's because you have extra electron pairs on these other oxygens, so that leads to that slight negative charge. But again, the key being that just like these are sort of like, just to show you, CF4, you can have very polar individual bonds, but if the molecule is symmetric, they're all going to cancel out and you get no net dipole moment. Whereas you can have a nonpolar bonds like O3, but if the molecule is not symmetric, it has that bent geometry that can lead to it being a polar molecule. So let's look at a few more examples. This is a table from your textbook. We've looked at a couple of these already. So we've looked at HF. We looked at H2O, we looked at O3, and these give specific values. So you can see, compared to something like H2O, ozone has this much smaller dipole moment. So it is still polar, but it's not very, very strongly polar. But it's a measurable amount, and it will orient itself in an electric field. Right, and we can look at another couple here with ammonia and phosphorus trichloride right here. These are both polar molecules because of, again, an imbalance in the electronegativities here. And these have tetrahedral electron pair geometries, but their molecular geometries are both trigonal pyramidal. Now, one thing we can see is there's a difference in the polarity. the values of the dipole moments are different. Nitrogen is more. There's a bigger difference in electronegativity here, so this leads to a more polar molecule in ammonia, whereas in phosphorus trichloride, the difference in polarity between the phosphorus and chlorine is not as big, and so we get a smaller net dipole moment. And so the arrows here also indicate the direction of the polarity. So our most polar is HF, but H2O is not very far behind in terms of the actual value. So oxygen is only a little bit less electronegative than fluorine. And as we move down to these other atoms and molecules, we see that change in polarity. So just to draw out our ammonia here, this will apply to the PCl3 just to show this. Right, we have this tetrahedral geometry for the electron pair geometry, but we have this lone pair, of course, on the top. And so we get this trigonal pyramidal structure that we've seen. And that leads, now that we've broken that symmetry of the tetrahedral, now these H's are different than this lone pair up here. And so all the dipoles along this direction all cancel out, much like we saw with water, but there is a dipole that will now point from the hydrogens to the nitrogens, right from the middle of the three hydrogens. So that net, the fact that they're all a little bit diagonal, means that these dipole moments don't all cancel out. And the same thing will be true for PCl3, except for the dipole will point in the opposite direction because the chlorines are more electronegativity than the phosphorus. All right, we'll continue to practice with this in class and look at some other types of molecules, but this is what we're looking for: imbalances in the ways electrons are shared, net over the whole molecule, and whether there's symmetry present or not. And so we will continue to look at this, and this concludes our section here talking about polarity of molecules.